Hello and welcome once again for another example problem. We'll be using the tables again, and we'll see how to find things, a couple of different ways for interpolating and things like that. Okay, so let's jump right into it. So using the tables for water, determine the specified property data at the indicated states. Now we're going to discuss some of these properties later, but the process for finding them is all going to be the same regardless of what the property is that we're looking for. So we may as well just do it even though some of the properties we're not familiar with. In each case, locate the state on sketches of the PV and TV diagrams. Okay, so part A is P, this is for water, of course, as it says, is for P equal to 2 megapascals, T equal to 300 degrees Celsius, and we want to find the specific internal energy, lowercase u, in kilojoules per kilogram. Part B, you can read this, 2.5 megapascals, and so on. Okay, now I will note that here, this one actually is in English units, and your book uses E at the end to represent English units. So like table A2E, for example, with an E on the end, is the English units, and just plain A2, table A-2, would be the SI units. So this is how you'll find each of these tables. Anyhow, let's jump right into it. So for part A, what I'm going to note is we had P equal to 2 megapascals, and T is equal to 300 degrees Celsius, and we want to find U. Okay, here, if we go here, what we'll find, let's say we went to table A3, for example. What we find is that the temperature T is greater than the saturation temperature. So we should immediately note that this implies, of course, if the temperature is greater, that we're in the superheated region. You could also do this with the pressure, right? If you wanted, if the pressure was lower than the saturation pressure, we would also note that it would be in the superheated, right? That would be table A2. Okay, so we know that it's in the superheated region. Great. So let's use superheated table. A4. Now, if we go here, I'm not going to actually pull up the table. I'm going to let you go and examine this. But if we go here, what we're going to find is that we have specific values at the pressure. So at 2 megapascals, what we find is that no T equal to 300 degrees Celsius on table. So we need to interpolate. And this is going to be good because we're going to need the practice. So here's what I'm going to do. I'm going to read off the values. We do have, I'm going to call it T naught, which is going to be at 280 degrees Celsius. T1 is going to be 320 degrees Celsius. So we don't have 300, but we have 280 and 320. So we have two values that are right around that, which is great because we need that for our interpolation. Also, corresponding, we also know that U naught, which is also, we can also look right on the table, if you go right across from the T naught, you'll find U naught, and that one was equal to 2736.4 kilojoules per kilogram. So make sure that you actually go check the tables and verify that my numbers are correct. U1 is equal to 2807, because this corresponds to T1, 2807.9 kilojoules per kilogram. Now, how do I do the interpolation? Basically, remember before we discussed how you do this, how you do, you set it up as if it's a line and so on. As dependent variable. So what we want to find is we want to find u. So let's set that as the dependent variable. We're going to say u. Okay, and that's going to be equal to, well, the independent variable is going to be the t. Okay, this is just the easiest way to do the interpolation. So u is going to be equal to m times t minus t naught. Now, plus u naught. Oh, that's amazing, right? U is going to be equal to that, because note that, we have this form, right? Y minus y naught is equal to m times x minus x naught. This is the exact same thing. I just added this term over to this side, right? But I do need to find m, and m obviously is the rise over the run, or the dependent variable divided by the independent variable. So m here is going to be equal to u1 minus u naught over t1 minus t naught. So that's going to be equal to, well, we have these values, right? We have 2807.9 minus, hold on, and this is u naught, which was 2736.4 that we read off the table, divided by 320 minus 280. Okay, and I'm not going to actually find that value. I would store this in my calculator, which is what I actually did, and use the m in this equation. So then the value is going to be equal to m, which is this thing, times t. Well, t is the value that we wanted to find it at. We wanted to find it at 300 degrees Celsius, so 300 minus t naught, y naught, 280, plus u naught, which was the 2736.4. Now I'm going to move this table down a little bit here. It's going to go on to the next page, which is fine. That means that what I find is that u ends up being approximately, anyways, if you use this value, u ends up being approximately 2772.2 kilojoules per kilogram. So that's my value. So this is how we interpolate. And I'm going to do another example of interpolating, and we're also going to do one with, as you'll see, with a quality. Okay, so the quality being 50%, but that's going to be next. Let's draw this on the table. Okay, so we have the PV table. That looks something like this. They both look pretty similar, by the way, but that's fine. So we know that the pressure that we're looking at here is 2 megapascals, and it's in the superheated region, which means it's over here somewhere. And basically, if I were to draw, this is the isotherm at 300 degrees Celsius. I should have put this up here, sorry. Should have been up there. And that's obviously at 2 megapascals superheated. Also on the TV curve, we can do the same thing. And it's a similar curve. You know, I'm trying to make it look a little bit slightly different here. But obviously this is at 300 degrees Celsius. And the pressure in this case goes something like this. Once it goes across, and then it comes up here, and this is where it would fall. And this is the isobar of 2 megapascals. This isobar. This line that I drew here, that's an isobar. Okay? And obviously the point, again, still in the superheated. It's on the right-hand side of that curve, so we know that that's the case. Okay, very good. How about B? B, it turns out that we can read B right off of the tables. So what we find, I probably should move this table down. Actually, I don't need this table at all. Sorry. B, we find that T is less, the temperature is less than the saturation temperature. So this implies we're in the compressed liquid, which means table A5. And we can read the values. We can read the value. We find U, which was what we were looking for, is 849.9 kilojoules per kilogram. Okay, so the idea up here, 2.5 megapascals, 200 degrees Celsius. We can read that right off of table A5, and we find that U, in that case, is 849.9 kilojoules per kilogram. Great. Now C. Oh, let's draw the plot, shall we? PV. We know that it's in the compressed regime. The PV and the TV look kind of similar, but we do have to keep track of what it is that we actually have here. So over here we have 2.5 megapascals, and this is obviously in the compressed region because it's on the left-hand side of this curve. And the isotherm related to that looks something like this. This is the isotherm at 200 degrees Celsius. Alternatively, for our TV diagram, again, we have a curve that looks something like that. And we know that the temperature is at 200 degrees Celsius. And we have this nice looks something like this. we have this nice isobar, 2.5 megapascals. Okay, so that's how we can identify the state. Again, it's in the compressed region on the left-hand side of the graph. Okay, how about for C? C is asking, okay, so now we need the English tables, and we know it's a mixture now because we have the quality here, which is 50% or 0.5, right? So if we go to the table, which table is a good question. It's table A-2E, because that's the English units table. And this is the saturated table, right? Because it has to be saturated if it's in the mix. It has to come from the saturated table if it's a mix. So that's good. And we do have like a nice little formula for this. We had something that looked like this. V is equal to VF plus X times VG minus VF, right? We had something like that. Well, it's the same idea for U. U is going to be equal to UF plus X times UG minus UF. And these are going to be the gas, which is the vapor side, and the liquid, which is the fluid, right, F. So we have this nice little formula. We can use the exact same thing. And what we find is UF from the table is equal to 137.95 BTU per pound. UG is equal to 1065.4 BTU per pound. And of course, X is equal to 0.5. Even though it's 50%, we have to use the decimal value. So U has to be equal to 137.95 plus 0.5 times 1065.4 minus 137.95, which is equal to 601.7 BTUs per pound. So that's our value for part C. Okay, so this is how we would do one with a mixture. Okay, very good. It's similar to the interpolation, but we're doing it in a nice way because we know the quality, right? So we can use that fact to help us. How about this one? Again, we're in English units, so we're going to have to determine where we lie. And we find that for part D, we find that the pressure is greater than the saturation pressure. What does that mean? That means we're in the compressed region. Okay, since we're in the compressed region, then compressed liquid region. Well, we could use the compressed table, but in this case, the pressure is low enough. Use the saturated liquid value, right? Because it doesn't change a whole lot from that. So H is going to be approximately equal to HF, and reading off. Now you have to be careful with H, by the way, with the tables there, because there's also something that goes in between. It's the evaporation in between the saturated liquid and the saturated vapor. So the enthalpy table, you have to be careful. There's 3 rows, And typically we're going to want to take HF and HG, but not the HFG. So be careful there. But anyways, reading off, we find HF, or H is going to be approximately HF, which is 269.7 BTU per pound. So please do go to the tables and just make sure that you can see this. This is, I should write table A2E again. Okay, so the English units table. And the plot for that, well, you can obviously imagine. This is in the compressed region again. Oh, by the way, I think I missed the plots up here. This one, let's make a little plot. The PV, oops, looks something like this, and it's going to go right in between, halfway in between. Okay, and it's going to be the same thing for the TV, because it's a 50-50 mixture. It's got to be halfway in between. Okay, so it's going to be in the half mix. So it's in between the curve there. Not on the right, not on the left, but in between. And by the way, if there was a value that was actually a saturated value, it would land right on the curve, right? So we can keep that in mind. Okay, so for this problem, though, for this one, we knew it was in the compressed region, so immediately you should think, okay, it's going to be on the left-hand side of this curve. It's going to be somewhere in here, maybe. And the isotherm will look like that. And over here, same idea. It's going to be something like this. Okay. So this is going to be our plots. Okay, then the final one is part E. Now, let's go back up and see what part E was. Well, part E was at 1.5 megapascals, and we're given the specific volume here, which is 0.2095. Now, what you can do is you go up and you look at table A3, and we note that the specific volume actually is greater than the specific volume of the vapor, Vg. So this implies we're superheated. So use A4. Okay, but when we go to table A4, again, we find, unfortunately, that we don't have the exact value. So we're going to want to go around this, find values near V equal to 0.2095 at P equal to 1.5 megapascals. Okay, so we're going to look for that, and what we find is V, I'm going to call it V naught, is equal to 0.2030, which is obviously smaller than that value, meters cubed per kilogram, and V1 is equal to, so the one that's just above that is 0.2160 meters cubed per kilogram, and the corresponding value H naught is going to be equal to 3255.8, and H1 is going to be equal to 3342.5. These are kilojoules per kilogram. Okay, so those are the enthalpy values. And again, we'll talk about enthalpy soon, but it's going to be the same process for this as it is the internal energy, the specific internal energy, and so on. So now again, we want to find H. Remember, going back up to the problem, we want to find H. Since we want to find H, that's going to be our dependent variable. So we're going to set up an equation that looks like H is equal to M times, what was the dependent variable? Well, that was V. So V minus V naught plus H naught. That's what we're going to get. Now we need to find M. M, of course, is the rise over the run, so it's going to be H1 minus H naught. That's going to be my dependent variable over my independent variable, which is V1 minus V naught. So obviously that's going to be the same as 3342.5 minus 3255.8 divided by 0.2160 minus 0.2030, and then the value that I was looking for around was this one, 0.2095. So that means my equation then is going to be H is equal to M, which is this thing, right? I'm going to save that in my calculator so I can, get as accurate as a estimate as possible. The V that we were looking around was 0.2095. V naught is 0.2030. And H naught was 3255.8. Okay, so if I take that M, I multiply this thing out, what I find is that this value approximately comes out to be 3299.15 kilojoules per kilogram. Okay, so that's how we interpolate, and I just gave a couple of examples, also ones with quality and just reading off the table. Hope that helps. See you again next time.